We've covered the key points about limits at finite values of x. There are a couple of specialty topics we now want to add, and the first one is one-sided limits. So let's take a look at, let's get a little space here, and let's take a look at a function that looks like, let's say this. Okay. We're interested in understanding the limit right here. Let's say this is, I don't know, pi. We want to know the limit as x tends towards pi of whatever this function is, f of x. And by this function, I'm talking about both pieces. So does this meet the definition of limit? Is it the case that if by getting close enough to c in x, but never touching, then the height f of x gets as close as I want to one particular value L? If that's true, then we know the limit exists. Well, the problem is, as we get closer from this side, the height's going one way. As we get closer from this side, the height's going to a different place. And so no, we are not getting close to one particular value L. And therefore the limit does not exist. Does not exist. But there are functions like this that come up often enough that there's a need to describe something similar to a limit. Now let's talk about that. I want to remind you about what you know about what's called the greatest integer function. So the idea is 1.738. What is the greatest integer contained within this? Well, it's 1. Now if I give you a number like 4/3, what's the greatest integer contained within that? Well, again, it's 1. What if I give you the integer 2? Greatest integer contained within that is also 2. Now here's a tricky one that students often make a mistake on, so be careful here. What's the greatest integer contained within negative 1.9? It's actually negative 2. Remember, the greatest integer function is the integer, the largest integer that is less than or equal to that value. So be sure that you understand these two special cases. Now, notation-wise, we represent the greatest integer function sometimes like this, int of x. Sometimes it's just represented like this. Note the difference. These are square brackets. This is not the same as absolute value. And some books, to further emphasize that point, will use this text. Finally, your graphing calculator has the greatest integer function in it. It's int x. You find it in the catalog, second 0. And then you just type in I to scroll down to the i's. There's int x, and its graph looks like this. I've brought it up here just to give it a little more definition. Let's zoom in a bit. So notice that, for example, the greatest integer of 0.5 is 0. Greatest integer of 1 is 1. Greatest integer of 1.99999 is 1. All right, well, all of that said, the greatest integer function is the best example of a motivation for something besides this classic definition of limit. As we approach 1, if we get close enough to 1 in x, does the height get as close as we want to one particular value? The answer is obviously no. But if we only consider this part of the function, namely values that are less than 1, then clearly we are satisfying the definition of a limit. And so it's for that case that we define a kind of consolation prize for certain functions. Yeah, you didn't win, but we're glad you came anyway. here's something to remember us by, and that's a one-sided limit. We'll say the limit as x approaches 1 from values that are less than 1. That's what this minus sign means. Of the int function, we'll say that that limit, that one-sided limit, is 0. And similarly, the limit as x approaches 1 from values that are greater than 1, the limit of the int function is 1. That's what one-sided limits are about. Now, one could quibble with the fact that maybe this is not the best notation because it doesn't have anything to do with being negative. It really means less than. But this is not the first time we've encountered bad notation. Similarly, this really means greater than. So we're just going to have to deal with that. Keep in mind. Again, these are not true limits. They are just what we want to call one-sided limits. And for example, these come up in another instance, and I will just try to sketch it quickly. Let's get rid of this and this. And let's draw this function here. How about, let's say this is the square root of x plus 2. Notice that at -2 it terminates. Well, can we even talk about the limit as x approaches -2 of this function? What's the limit as x approaches 2, or -2 of the square root of x plus 2 function? No, we really can't talk about it because it's outside of its domain here, and so we can't get as close as we want to this one point in x from either side. But because we can approach it from numbers that are greater than it, we can say that the one-sided limit exists. And remembering that our definition of limit has nothing to do with the actual value at the point, or at least it need not have anything to do with the actual value at the point, we could even talk about this limit as being well-defined, even if the function wasn't defined at that point. That would be a slight variation of the square root of x plus 2 function. I'll leave that as an exercise to the reader to figure out what function that would be. But again, the limit is perfectly well defined if we're willing to constrain it to this one-sided limit. I guess the last thing I should point out is, in a sense, we've already been dealing with one-sided limits previously as we looked at limits as x approached infinity or negative infinity, because unless you're Buzz Lightyear, you can only approach infinity from the less than side. So that's a kind of one-sided limit.